Hello everyone, good evening. Just tell me once if I'm audible. Just write it in the chat box, it's fine. Am I audible? Okay, thank you. So, welcome to the 7th weekly live session for the course Earth Sciences for Civil Engineering, Part 1 and 2, which is taken by Professor Javedan Malik from Department of Earth Sciences, IIT Kanpur, and myself, Ananya Mukherjee, from Department of Earth Sciences, IIT Kanpur itself. So till now we have talked about the rocks, minerals, different geological structures. We got a brief overview about all the natural hazards that are necessary for us to know about in terms of civil engineering. And we also learned about earthquake and how we can mitigate that hazard, how we can minimize the risk. We learned about different kinds of techniques, how we can study past earthquakes, how we can study active faults that are still deforming the earth, and how we can get all that information and try to reduce the hazard that earthquakes are causing. So with that, now we will move on to the very important next topic, that is the role of geological structures in civil engineering. So geological structures are what? They are folds, faults, joints, okay, and also the role of the kinds of rocks that we have, that is igneous, metamorphic and sedimentary. The role of these rocks in different large civil engineering structures that we have, that is necessary for us to understand how to identify the sites, how to identify what kind of support is needed, what kind of materials are needed to strengthen the structures that we are building over there. So first we will start with the structure of dams. So over here, as you can see, this is a very simplified structure of dams, of a dam, sorry. So because of the structure over here, you have two kind of forces acting here. One is the weight of the dam, okay, and the T is the tensional force, and you have the resultant of this, okay. So now as you can see below, we have a folded structure, okay. This is a fold, okay. To be precise, this is a syncline, okay. So how do we know whether this is a syncline would be if we knew the ages of the rocks over here, okay. So if the youngest forming rock is in the middle over here, then it would be a syncline, okay. So for now we will call this a synform. This is a folded structure, okay. So these arrows that we see and these planes that we see, okay, these are the bedding planes, okay. So bedding planes, as in these are, suppose say, different rock beds, okay. These rock beds are made up of different rocks. They could be similar in the types, as in all of them could be sedimentary rocks, all of them could be say metamorphic rocks, or you could have different rocks also over here. So right now we are just considering a general case. These are rock beds over here. This is your reservoir, okay. This is the upstream direction, this is the downstream direction, okay. So now we can see that suppose there is some seepage, okay, due to the reservoir water over here, okay. So the water will start seeping through these bedding planes, okay. These planes are actually planes of weaknesses, okay. The because there is a plane of heterogeneity between these two beds, these planes are usually are usually plane of weakness. So if water starts percolating along these planes, then the structure, the dam structure is not affected, because the direction of the percolation of water is going away from the dam structure, okay. And also if you see the resultant force, the resultant load that is being exerted by the dam structure over here, that is perpendicular to these bedding planes, and that is why this kind of a geological setting will provide the best resistance against the load acting on the geological structure that is present here. So now we go to the next case. Next case is, this is again a synform, a folded structure, okay, but as you can see that the over here the beds were dipping away from the resultant force, and also in the other direction, the upstream direction, okay. Now the folds, the bedding planes, okay, and the resultant that is created by the dam, the resultant load that is created by the dam, they are both in the downstream direction, okay. So over here as you can see, resultant is parallel or nearly parallel to the bedding planes. So the leakage that would be caused by the reservoir water will seep through these bedding planes, okay, and this will create instability in the structure of the dam over here, okay. So if the bedding planes are dipping in the downstream side, this will be a problem for the dam structure over here. Now we will consider different kinds of bedding plane inclination and the effects that they have on the dam structures. Over here you can see these are vertical beds. This is a very idealistic situation. Usually such vertical beds are, they are very rarely found, but suppose we are considering it, okay, so it will not really cause problems in creating an uplift pressure, okay, for the dam structure, but there will be seepage, but the seepage will be kind of uniform, so the instability is reduced. It's there, but it's slightly reduced. While if you see a steeply inclined bed, and also again this is again in the downstream direction, okay, so this condition is very disadvantageous. This is not at all suitable if your geological area has such steeply inclined beds. Suppose we have horizontal beds, okay. So this, if you see, then this would be a slightly suitable area, okay. You can kind of use some support, use lining and some other supportive structure over here to make this a more suitable area for your construction. There will be seepage again, okay. So since this is a horizontal bed, okay, so the seepage would be in the horizontal direction. So it's there, but it's minimal. So as again this would be a partly suitable geological setting, okay. Now if we consider faults and dams, okay, so if you see that this fault, the black one and the orange one, okay, so these are situated away from the dam structure over here, okay. So and also considering that if these are not active, okay, like right now these are not active, deformation is not happening along these faults, okay, so only then that these would not cause damage to the dam structure, okay. But if we have suppose such faults over here, whether they are active or not, it will still cause damage, because as we have seen before, seepage and water percolating along these weak planes, okay, so this will again reduce the stability of the dam. Now we come to another major structure or civil engineering feature that we build, that is the tunnels, okay. So tunneling, you need first thing that for tunnels is necessary to understand is homogeneity and heterogeneity, okay. So if there is more homogeneity, obviously I'm saying more because absolute homogeneity finding it in nature is very difficult. So if there is more homogeneous nature, it is more suitable to build tunnels over there. So over here now we are considering tunnels and different rock types, okay. This is a plutonic as in rock examples would be say granite, pegmatite, okay. So suppose this is a plutonic igneous rock and this is a volcanic igneous rock. Volcanic igneous rock means say basalt, okay. So basalt is one of the most common examples that we have, okay. So over here we can see that, and there are these different joints, okay. See these dashed segments are actually joints. Okay, so both of these are jointed, and you can see there are few horizontal beds in the volcanic rock also. Now these are ash beds, and these are also these can also be considered as weak plains. Okay, weak bedding plains again. So we can see that the crisscrossing joints will also play a role over here. But if you consider igneous rocks are probably the best suitable area where you can have tunnels. And volcanic also, they are good, they are well suited, but any plains that you have, like suppose these joints, okay, so basalt, if you talk about basalt, they are very prone to weathering. Okay, so they will weather very easily along these weak planes that are the joints. So we will have to use suitable lining method and roof support method over here. Some of them are like say grouting or bolting. Okay, so we have to use these to support these structures, okay, when we are considering a volcanic. Metamorphic rocks, again the ones that are non-foliated. Which one were the non-foliated ones? Marble and quartzite. Okay, so marble and quartzite, why? Because their chemical composition is kind of uniform. Okay, so the quartzite is made up of silica quartz, okay, and marble is made up of calcium carbonate. These are examples. Okay, so if you are building one through quartzite, it will be very suitable. But any non-foliated rocks like say schist or slate, they again, the foliations that they have, because they are called foliated or metamorphic rocks, so the foliation planes are again planes of weaknesses. So you can have damage to the tunnel structure because of the existence of these types of rocks. And sedimentary rocks, again there is it depends on the chemical compositions. Like if you have siliceous and ferruginous sandstones, they can be suitable area to build tunnels. But suppose you have shale or very loosely formed sandstone, not very well packed, okay, so not well compacted sandstone, then those are not suitable. Limestone, though it is compact, but because owing to the chemical composition, okay, and owing to the property, the characteristic that it has, it can dissolve very easily with continued interaction with water. You will have caving. Okay, so there is something called caving that is relatable to the limestone areas. So if you have limestone, it will cause caving, and then you will have again a very weak supported tunnel structure over there. It is not suitable. Next we come that we have, suppose these are good suitable rocks, okay, but this layer is being weathered. Okay, so closer your tunnel is to the such weathered surfaces along a slope. Okay, say suppose this is a slope. Okay, so along the slope, close to the slope, then there is a chance that the weathering might reach your tunnel structure soon, and then it will cause damage to the tunnel structure. Next we move to tunnels and rock attitude. What is rock attitude? The orientation of the rock beds. Okay, so if you remember, we had talked about strike and dip of the bed. Okay, so if we are considering horizontal beds, okay, so the dip is 0 over here. Okay, there is no dip. These are horizontally occurring rocks. Now, but even if they are horizontally, you would say that these are very good areas for construction of tunnels. Obviously they are, but again you have to keep in mind the homogeneity and heterogeneity existing in the area. Over here, since the entire the tunnel is running across one single unit of rock. Okay, the entire rock component is the same along the length of the tunnel. Okay, so it is a homogeneous area over here, and this would be a good place. But if you look at the B diagram, you can see that the tunnel is it is facing three different strata, three different rock beds. Okay, so then you will see that there is heterogeneity. Okay, but since the heterogeneity is, along the sides of the tunnels, you can easily, use lining, okay, and you can support this structure. But again, since when you are, identifying your sites for such structures, you have to take into consideration the different beds, that rock beds that are present over there. As over here also it is mentioned that the tunnel, should lie along the strongest available rock, so it has the proper amount of support, so it does not cause, damage in future. Okay, so they were horizontal beds. Now we move on to vertical beds. Okay, again, finding exactly ideally vertical beds is, pretty rare, but suppose, you have very steeply inclining beds. Okay, so when we are dealing with tunnel, again, as previous slide you saw the example, the A case. You can see over here also, this case A also shows that the tunnel is going through one single rock unit, okay, one single rock bed. So this again would be a suitable, much, you know, better, it would be a resilient structure for you, and you can, favorably you can build a tunnel across this such a setting. Okay, but when you see in the case B, okay, so there are different kinds of rocks that are, that the tunnel over here is going to face. Okay, you have one rock unit, then you have more rock unit, then you have one more rock unit. Okay, so there are three different rocks, and then you can see there are more planes over here, these lines over here. So these can be bedding planes, okay, or these can be, probably joints also. So you can see that there is a lot of heterogeneity experienced by the tunnel over here. Okay, so then this again is not a very favorable condition for us to build a tunnel. Now in the next one we are going to consider inclining beds. Okay, now suppose they are dipping towards left or dipping towards right. You can see that the load, okay, so suppose, these planes, these are the planes of weakness, as I have mentioned before. So there is either movement or there is seepage, and also if you consider the forces that are acting, you can see that the resultant is also going to, make, it's going to cause the loading on only one side of the one face of the tunnel or one side of the tunnel. Okay, so then you would have to make arrangements to support this side of the tunnel, okay, so that the load is not exceeding and the tunnel structure is not damaged. And similarly over here you would have to, provide support on the left side of the tunnel over here, because as you can see, due to the dip being, towards the right, all the load is going to be experienced by the left wall of the tunnel. So you will have to provide support over here. Okay, then now you see that suppose you have, okay, you have to build a tunnel and it has to go through different rocks. Okay, but then which side do you, start excavating from? Okay, because the dip over here is suppose towards south. If we consider, this direction as north. Okay, so suppose this is your north, okay, and this is your south. So your beds are dipping towards the south, okay, and you are trying to excavate from here. Okay, so this is excavation against the dip. Okay, so this is going to be slow, this is going to be, problematic, because, suppose you're excavating and one of the rock beds, suppose the plane of, the bedding plane is pretty weak, it has been already damaged. Okay, so the rock might, slide, and then you would have a problematic condition over there. But in the B, case, we can see that the, the rocks are dipping towards the north. Okay, they are dipping towards the north. So if you start excavating from here, okay, that is in the direction of the dip of the bedding planes, okay. So it is easier compared to the case A, and also it is ideal then. Next we will see, now we spoke about very one kind of a condition only there, like suppose there is just just inclined beds or vertical beds or horizontal beds. Now suppose you have a fold structure, okay, a big area which has more folds, okay. So now if we have to build a tunnel over there, okay, so now we can see that these are suitable at certain areas, okay. Suppose we are talking about the anticline, okay, so this is your anticline, okay, and because of the anticline, okay, this is the crest of the fold, okay. So the crest of the fold, because of the bending that happens along the crest, a lot of jointed structures are formed, okay. And if you build a tunnel here, these joints, as we have mentioned before, these are planes of weaknesses, okay. So this would have a very weak roof, okay. The tunnel roof would be very weak, and there are high chances of any of these planes causing a slippage, and you would have a very terrible accident over here or in future if you build it along the anticline along this area. Now if you consider the syncline, okay, syncline or synform, this is obviously this could be an anticline or this could be an antiform, okay, depending on the age of the rocks. So now if we consider this synform or this convex downwards structure, if you build your tunnel through the the trough part of the fold, okay, crest, this is the crest, this is the trough. So again, as you see that the beds are all dipping over here, okay, and due to the bedding planes, they are dipping towards each other, any kind of interaction with water and seepage and percolating along these weak planes, they are going to cause problems for this structure. Now if you suppose you build your tunnel through the limb, okay, this is the limb of a fold, this is a limb, this is a limb, this is a limb, okay, these are limbs of the fold. So this over here, you can provide support on this wall, as we had seen before in the inclined beds, okay. So if you provide support and lining along this wall, you can cause you can give it support against the load that is being created by these inclined beds, okay. So this would be most suitable when you are considering such a folded area geologically. Now there is another example of how you could experience a folded structure over there, and you have to build a tunnel, okay. Over here you can say that this is the fold axial plane, okay, this is the axial plane of the fold, and the tunnel is parallel to that axial plane, okay. But when we are considering here, okay, so the tunnel is actually going perpendicular to the axial planes of these folds, okay. So the fold is again along this axis, and this tunneling is going perpendicular to that. Now due to this kind of a setting, you can see that the tunnel has to go through the crests and the troughs both, and it will also it will meet different types of beds over here, okay. So different types of beds, again as I have mentioned before, it will create heterogeneity. Heterogeneity is not good for our civil engineering purposes. So this is not at all a good way to build a tunnel when you are drilling perpendicular to the axial planes of the folds. Now we will consider faults and joints, okay. So suppose you consider case A, okay. So this is a fault, as I have explained the terminology before also. The one below the fault plane is called footwall, the one above the fault plane is called the hanging wall, okay. So you are building the tunnel from the hanging wall side and you are going through to the footwall side. Now if this is not active fault, it is fine. Okay, you can just, where the tunnel is intersecting the fault plane, you could provide lining and bolting and other support systems along the roof, along the sides, and it will hold. It is a tolerable situation. But now if you consider the case B, okay, and the fault is running parallel to the length of the tunnel, okay, so the entire plane of weakness is along the top of your entire tunnel length. Okay, so this is not at all a suitable condition. There would be planes of weakness, there could be movement over here, so it will cause problem. There can be seepage over here, and also because of the existence of the fault, and due to maybe past movements, there would be some crushed rock over here, which is loosely it is loosely bound, and that is why it will again create a plane of weakness over here. So this is not at all suitable. Now we have case C. Okay, case C, this is your fault. Okay, this is your fault, this is a fault plane, and you can see that the tunnel that we have shown here is in the footwall side. Okay, this is the footwall, this is the hanging wall. So now the tunnel is at the footwall. Okay, and you can see that the movement of the hanging wall is downwards. Okay, so slightly we have avoided the fault over here. And also considering, suppose in you have made different studies and measurements in this area before, and you see that the deformation is mostly only on the hanging wall side, it is not on the footwall side. So this would be a safe option for you to build your tunnel. Okay, so as we have seen here, the shift is made towards left of the fault, so as tunnel is founded in the foot wall, foot block. Okay, and it will avoid the fault that is present here. Now suppose consider there are joints. Okay, so if there are joints which are parallel to the tunnel axis, I'll just use the pen. Okay, so suppose this is your tunnel axis. Okay, and the joints are also suppose they parallel to this. Okay, this would be undesirable. Okay, because again if they are along the length of the tunnel length. Okay, so it will cause seepage and it will cause planes of weaknesses to be further damaging later on. Okay, but if we consider this, okay, so the tunnel length is like this, but you have joints like this. Okay, slightly almost perpendicular or oblique. Okay, so wherever such joints are met, okay, wherever these are intersecting the tunnel structure, you can provide support and kind of lining over there to avoid future damages. Okay, so it is not the best condition, but it is tolerable and we can work with it. So now we understood all the different kind of geological structures and how they how studying them and identifying them, how we can choose the most suitable option for us. Now we have learnt about earthquake hazard. Okay, so now we will move on to different hazards and how they how studying them, understanding how they are occurring, and how we can mitigate these hazards, how we can minimize the risk over here, how we can create a warning system and prediction, forecasting. So we have learnt that about earthquakes. Now we will move on to different hazards. So the first one would be tsunami. As you all know, tsunami wave is different from the normal wave due to the height, due to the energy that it carries, and mostly due to the mechanism by which it is caused. Over here you can see, okay, so the initial, okay, so initiation of the tsunami is primarily due to any kind of tectonic movement happening in the ocean basin. Okay, mostly these tectonics are caused due to earthquakes. That is due to plate movement, tectonic plate movements. If you remember, we had talked about convergent boundaries, divergent boundaries, transform boundaries. Okay, these are also faults. Convergent boundaries are mostly they are colliding Then you have the divergent boundaries, they are moving away from each other, and transform, they are sliding past each other. Okay, so all these actually create very large areas of weakness, large areas of fault planes, where subsequent movements and subsequent kind of deformation is going to create ground shaking instances. Okay, so tectonic, so over here as it's mentioned, it's earthquakes and or ocean floor volcanoes will happen when you have divergent boundaries. Okay, so the plates are moving away from each other and mantle material comes up and you might have an ocean floor volcano. And earthquakes, suppose they are colliding or they are moving past each other, so those are causing earthquakes also. Okay, so because of this, the water around such area, okay, around this point where the tectonic movement is happening, the the water starts displacing itself. Okay, then once the tectonic movement has happened, the water is displaced, then the energy is going to, yeah, so the energy is going to cause the water around to move in the areas near it. Okay, so your tectonic instant happened here, the water over here got displaced and now it will move to the surroundings. Okay, then it will travel towards the shore. Okay, so the wavelengths of the tsunami actually continues to grow, okay, as the the time increases. Okay, and you have the subsequent crests and troughs from which have started spreading out from here. They will start moving and they can also continue for hours. Okay, so suppose this is very much far away from the shore, as you will see in the examples later on. Okay, they could be very far away from the shore of the affected area, but because of the energy that it has and because of its characteristic of traveling, it can cause huge waves to strike the shore. Okay, then it starts traveling, the waves start traveling, then you have the approach. Okay, so the tsunami is approaching the coastline. Okay, and it will there is going to be collision of the rising the seabed over here is it is shallowing up. Okay, so the seabed is much more higher over here, so the waves are going to collide with the coastline, with the seabed that is present next to the shore. Okay, and then the last one is the impact. Okay, so the wavelength is compressed. Why? Because the the water is meeting the seabed over here. Okay, so the wavelength kind of minimizes over here and that creates higher amplitude waves. Okay, great waves, then they collide and they will cause the damage that we talk about when tsunamis strike these areas. So this is kind of just the main characteristics and main elements of the tsunami. As you can see, this is the maximum tsunami water level. This is where after beyond this point it will crash onto the shore over here. Okay, so these are some of the terms that are associated with the tsunami, and then we kind of calculate the tsunami energy. If you remember, we had I you know we could calculate the energy of the earthquake. Okay, so we could also calculate the moment magnitude from the magnitude of the earthquake. Okay, so then similarly we can also calculate the energy that is created by the the tsunami that we are interested in. So this is the the formula for it, where mostly we have to understand the height of the crustal displacement. This is the slip that we talk. Okay, so over here this tectonic movement, okay, it could have been a fault. Okay, if we suppose think that this is where the this is where the rupture took place. Okay, and this moved like this and this moved here. Okay, initially suppose this plane was here, okay, and now it moved downwards. Okay, so this slip, okay, so this amount which has moved down. Okay, so this height that we are talking about in this formula, okay, this is also the slip when we consider just the fault and the earthquake. And the area where the tsunami generating area is also the area that is being affected by the tsunami. Okay, so this is how you can calculate the energy that is released when tsunami is caused. Now we come to two very important examples. One of the the I think the Chilean tsunami is by far the most damaging, most destructive, and also the highest magnitude earthquake had happened, which caused the tsunami. It was, I think, around 9.5, if I'm right. Okay, so why and how this earthquake was caused is, you can see it from this diagram. You can see that this is between the ocean plate and the South American, the continental plate. Okay, so the ocean plate is subducting below the South American plate. So this is again a collision boundary. Okay, so there is this is colliding, and so this is a convergent boundary. Okay, plate boundary. So you can see that the ocean plate is subducting below this plate. So the the point of deformation is around over here. And these are some of the images of the kind of extensive damage that was caused due to this earthquake. Now if you see that this entire this line, okay, this line is the entire area where the two plates are in contact with each other and the subduction keeps happening. Okay, so this is a large area. Okay, but the earthquake that we are talking about, sorry, the earthquake that we are talking about, okay, so the epicenter is here, so the focus is going to be vertically downwards. Okay, so this is the epicenter of the Chilean tsunami earthquake. Okay, and you can see that while this is it's happening in the western coast of South America, you can see that this is the trajectory of the tsunami. Okay, so this is the trajectory of the tsunami waves, which is reaching all the way up to Asia. So you can understand that how great the impact of this earthquake was, that all the way from South American coast it reached the Asian coast. Okay, and that too these the numbers mentioned in the blocks over here, these are hours. Okay, so suppose the earthquake happened today, the effects of the tsunami was felt in Japan the next day. So you can see that the tsunami waves, okay, so that were created here, the effects have going on till the next day for hours. Okay, so this shows the immense damage and immense devastation that can be caused by a tsunami. Now the next example of one of the another second largest, if we say, it was, I think, magnitude of 9.3 earthquake was caused near over near, along the Sumatra Andaman area, the fault over here. There over here you can see the red line that is traversing over here. So you can see that these arrows are actually the movements of the Indian plate. Indian plate is moving this side also. It's partly moving. It's also subducting over here, and there are some micro plates also which are probably attached to the Indian plate. And this is the Great Sumatran Fault, along which the deformation had taken place. Now the importance of a Sumatra Andaman tsunami or the earthquake was, there were two different kind of plate movements that were there, and that is called decoupled fault. Okay, So you have this strike slip, okay. So the strike slip happened between two different plates, and there was an interplate thrust fault, okay, that caused both of them together caused such a devastating earthquake. So as you can see that there is an interplate thrust and there was a strike slip faulting which was occurring on the overriding plate. Overriding plate is this side, okay. The Sunda plate is, this is the overriding one, and this is subducting downwards, okay. And over here you can see the animation over here, the one to your left, okay. The red part is the uplift, okay. It's the uplift is the area which rose up due to the deformation that happened along the fault, and the blue area is the subsided one, which where the crust has gone down, okay. So this was the fault, and so this was the fault, and this went up and this went down, okay. So you can see that the propagation of the rupture, okay, so the rupture happened here and it traveled across the fault towards the north, and in the right one you can see that this is the how the evolution of the tsunami waves took place. You can see that the the rupture, when it started traveling, that was when the tsunami waves started forming, and then they started moving in both directions, okay. So you have generated near the tsunami waves that generated near the epicenter. So part of it propagated towards the Bay of Bengal, and the other part moved over Andaman and then traveled towards Thailand, okay. So this is these are the ways how the rupture travels, and how the tsunami waves also start generating as soon as the rupture happens. Now these were some examples, okay. Now we can understand whether any area has previously been affected by tsunamis or not by trying to understand the sedimentary sequences. What are sedimentary sequences? The sediments that are carried by the sea or the ocean, okay. How are they lying on top of past rock beds, okay. So that is what we call as sedimentary sequences, a sequence of different sedimentary beds, they are stacked on top of each other, and understanding the characteristic of each of the bed, we can try to identify at what point the tsunami had taken place, okay. And by understanding the thickness of the suppose the sequences that we are seeing, we can understand how we can try to understand how destructive it was, what was the impact of it. So to understand that, over here we can see, yeah. So this is a pre-tsunami condition where everything is stable. This is initial, okay. So you have offshore sediments here, this is near shore, and this is the beach, okay. And these are the buried sediments, so these are the the past sediments of past rock structure that is there. Now when tsunami happens, okay, so this is the incoming tsunami, okay. So the tsunami is happening, and you can see that initially, as we have also read before, that the first the when tsunami happens, the sea the level will first start decreasing, okay. So it will cause inundation over here, okay. Now since the incoming tsunami is it's traveling towards the shore, it kind of displaces the water here, okay. So it will rework the place where it had just caused erosion, okay. It will start again depositing the ocean, the sediments that are found in the offshore part. It will start being shifted or being brought towards the shore, okay. So it will start traveling here, and then you have the deposition, okay. Now what we'll see, that once the tsunami has receded, okay, there are no new incoming waves, okay. So now there will be a return flow of sediments. Now return flow, it will take up more of the beach sediments, okay. It will take that and it will start depositing it in the over the near shore sediments, and partly on the offshore sediments, okay. You can see this is debris flow, okay. This is a very kind of a mixture of whatever has been, being taken back by the water when it starts receding after the tsunami has taken place. Now post tsunami, okay, suppose right now we are trying to study, okay, whether this area has been struck by tsunami before or not. We will start taking sediment cores, okay. So this sediment cores, you can see that, there are different layers over here, okay. So we then study these layers. We try to understand the texture of these layers. Now if you see over here, a beach will have very coarse sediments, okay. Near shore sediments will be finer than the beach sediments, okay, but coarser than the offshore sediments, and offshore sediments will be very fine in nature, okay. So similar characteristics we will judge from these sediment cores that we take, and we can also do, as in the previous lecture I had talked about trenching. So if you do trenching, you can try to see what kind of sedimentary sequences are there, and you try to understand from that. So this is one way where we can study past tsunamis, and then try to suppose it's a recurring phenomena over there, in that place. Suppose tsunamis happen every other year or something like that. So the sedimentary sequences that are there, it can also tell us the frequency of how often this area is being affected by tsunamis. Now another way that we can study past tsunamis is using corals, and understanding how they are growing, their shape, okay. So this is an example of how a geologist is measuring the height of the coral over here, and this is due to this coral has been exposed on top of the surface because of the 2004 Sumatra Andaman earthquake, okay. So due to the tsunamis, okay, a lot of corals are damaged, and it can cause different kind of problems with the corals. It can destroy them, it can change their growth pattern, it can it will deposit a layer of sediments or sand on top of the floor on the corals, and it will obstruct their growth, okay. So these are some of the damage, destructive phenomena that can happen on corals due to tsunamis. So now if you want to understand the kind of sea level changes due to tsunami, we can understand by the way these corals grow. These are called porites, okay. So these are kind of circular looking corals, okay. So as it's given over here, the coral is growing upwards, but in hemispherical way outwards, okay. So there is a layer, then there is another layer, okay. So annually it will form rings, okay, and this will only happen at low tide level, okay. This coral will grow only below the sea level surface, okay. As you can see in B, as soon as the growth of the coral or the height of the coral reaches on top of the the sea level surface, it intersects the sea level surface, you can see that it will not grow on top, it will not grow vertically upwards, it will start growing sideways, okay. Next you see that over here, as you can see that it started growing sideways, okay. It started growing sideways, it stopped growing over here, but suppose there is a sea level rise, okay. uh, so suppose if we talk about the Sumatra and the Andaman earthquake, okay, so the eastern part of Andaman subsided, that it went low, and the western part of the Andaman area, so it went on top. So the eastern part which subsided below, okay, so the sea level will rise over there because it has now been submerged, it went down, okay. So over there you can see, like if you want to know which side has gone on top, which side has gone below, you can also judge that from the coral growth over here. You can see that they again start growing upwards, okay. So that means the sea level has risen over there, that area has subsided or it has gone below. Now if you consider a D, okay, suppose this was there in the western Andaman part, okay. Now because the western Andaman has been uplifted, okay, so the sea level has fallen, Okay, now when the sea level has fallen, you can see that this will not grow, this area, okay, will not grow upwards anymore. It will start growing towards the sides. Okay, so these structures, okay, the way these corals appear can give us an indication. Okay, so when the sea level rose, when the sea level dropped, whether that area has been, uh, uplifted, or it has, gone, or it has subsided. So corals are a very useful, element that can help us in understanding, like, past tsunamis, or even the current tsunamis, which side has been uplifted, which has subsided. Now we'll try to understand how, different kind of quantities, or different aspects of tsunami can be measured. So these that you see, these tubular kind of structures, these are gauges. Okay, so these kind of measure the, the, say, your sea level rise or sea level drop. They will measure that. You have different kinds of gauges over here. You have GPS wave gauge, which will give you locations. So suppose this gauge, because of occurrence of tsunami, has moved. Okay, so it will be detected that there has been a movement. Okay, suppose the movement, the displacement is very large, so then it can indicate there is a, a tsunami incoming. Then when you have bottom pressure gauges, okay, then you have acoustic kind of gauges. Okay, this will, start measuring. Suppose a tectonic activity has taken place over here. Okay, so due to the tectonic activity, whether this gauge is, pushed or on top, or it has, sunken lower because of the tectonic activity that has taken place over here, the acoustic signals will, vary from the normal. So then again, that again will give you an information about the change in the, sea level, change in the ocean floor, the depth. Then you have coastal also, where, it will, then again over here you can see acoustic or radar. This will again see the sea level change that might happen due to tsunami occurring. Okay, so including the seismic observations, as we have learned before, to understand earthquakes, there are seismic stations placed all across the globe. Okay, so they are monitoring the deformation that is happening along all the plate boundaries and any area which is very earthquake prone. Okay, so deformation is being monitored, and sea level observations, as I just explained, the different gauges that are present. Okay, so all these observations, all the information from there is going to generate a tsunami warning message. Okay, so and then for hazard mitigation, these things happen, prior to any tsunami occurring. Okay, so you create a hazard map, you create a earthquake prone zone, you create a tsunami prone zone. Okay, and then you have tsunami signs placed at places which, is very frequently affected by tsunami. So this is the hazard mitigation part. Then education and awareness. Okay, so these are conducted mostly by, communities and some NGOs. They kind of educate the population that is very easily going to be hit by tsunamis, any future tsunamis. Okay, so they also work in tandem with the warning system and the hazard mitigation. So considering the hazard mitigation and the observations that we have, that is, pointing towards occurrence of a tsunami, and then the education and the awareness that has been created before, you can create a tsunami warning message. The tsunami warning message will come from the observations, and all three together, okay, that it will kind of help the coastal community residents. Okay, so they will be warned that there is an incoming tsunami, and that will kind of, give rise to the evacuation processes that has been put in place by the state over there. So this is how we can try to minimize these tsunami, the hazard that is, that comes with the tsunami. So for that, again, we need to understand how geological structures are, are how they are going to behave, whether it's going how the rupture will happen. Suppose there are four shocks, okay, prior to the main earthquake that has happened, so we have to govern those, we have to monitor those, okay. And then, because as we have said that suppose we study over there, any past tsunami sedimentary sequences, that will again give you an idea whether that place has been affected by tsunami or not. So altogether these things are necessary for us to understand and try to minimize the risk that is associated with the hazard. So till now we have done earthquake, and today we did tsunami. Now in the next week we will learn about other hazards like landslides and floods, and also tsunami and earthquakes. Okay, so when they occur, a large a large number of properties being affected by it, okay. We can reduce the hazard mitigation, we can reduce the risk that is associated with that hazard, but totally avoiding it is not possible. But when we are considering, say, landslides, suppose as we spoke about tunnels over here, so understanding landslide prone areas, we can kind of build, or kind of design our civil engineering projects over there related to these, and we'll learn that how information or understanding landslide will help us in understanding how we can create these structures over there. So with that, today this is over. I will just again forward the information about the resources and the YouTube channel, where all of the the recorded are there, the prior ones are there, and today again it will be uploaded by tonight or at the most by tomorrow morning. I would suggest that you join the channel, subscribe the channel, so you immediately get the the notification that it has been uploaded. So if